We are continuing our exploration of aromaticity, and although most of the mechanisms for aromaticity are reserved for chapter 22, there is one or two mechanisms in 21. And the one we're talking about here is the Claisen rearrangement. Same guy, different reaction. So clearly the skeleton rearranged there. And it's in a family called a pericyclic reaction. But before we can do a Claisen, we got to set up a Claisen. So to do a Claisen, you need to have an aryl allele ether. What qualifies as aryl? Aryl. You got a benzene. There you got your circle with a highlighter. Yeah. That one, if you're going to do it that way, I like it because I can see the pi bond. And the allele in green. Allele. Not attached to an alkene, but attached to a carbon that's attached to an alkene. And when that situation is right, then the number of pi electrons is magical. Kind of like when we determined aromaticity. If you can get 3 arrows going around in a circle, even though it's not what we call aromaticity, it's got the stability of aromaticity. It's like the mechanism version of aromaticity. And it just means that number of pi electrons is just right for going around in a circle in the mechanism. And that's what that word means. Pericyclic, going around in a circle. Going around. Peri is around the periphery. The periphery of what? A cycle. Going around the cycle. Okay. First step is not new at all. It's ancient. Base. pKa of the acid here. Don't say 17. 10. It's a phenol. And you just drew me, what, 5 different resonance forms of the phenoxide, the conjugate base? Huh. Because you could do that, that means it's easy to take the H off to make that base. Let's do it. Lone pair grabs H. Sigma becomes lone pair. You got the species that we have right here. You don't have to draw me anything. Apparently, we have to calculate pKeq. 10 minus H2O is 16, right? KEQ wasn't asked for, but if it was, 10 to the 6th. So there's a nice way to take the H off of a phenol. And that next reaction, what would you have to call that? That's an oldie but a goodie too. First one was chapter 4. Chapter 4, acid base. Chapter 10. You got a primary RX. SN2. Use your nu for an SN2. And you get the result that's drawn. Yeah, the setup for these things is pretty easy. They're very easily made ethers. And the best part is you're making a carbon-carbon bond to benzene here. That is not easy to do. So this is a nice reaction that lets you do that. And it looks like the new carbon-carbon bond ends up ortho to the O. Yeah. If I give you the intermediate, could you give me the arrows that get you there? Here's your intermediate. Can you get me there from the original? Yeah. You mean that, like that?
Yeah.
I'm thinking, well, it'll work. I can get that to work. She said resonate into there, resonate to there, come down here. I got no problem with that. That gets you there. I'm just thinking, do you like that better or do you like this better? I mean, they both get the same result. And the only reason I like this one better is that first arrow on the left generated a cation right next to an oxygen with a lone pair. I have no problem with your arrows. I would have given them full credit. And that gets you to the intermediate we drew here. And sometimes we get the opposite of what we learned earlier. This is tautomerization. But I thought it always favored the ketone or the aldehyde, the one that has the carbonyl. And normally that's true, because that pi bond is normally stronger than a C-double-C pi bond. Correct? But you just learned something about this new word. And let me tell you about the aromatic stability blows the other stabilities out of the water. So forget about, if I have a choice between making a pi bond between two carbons compared to between a carbon and an oxygen, I'm going to prefer the one to oxygen. That's just electronegativity based thinking. But if I have two species and one's aromatic and one's not, forget about what I just said earlier. That difference in stability energy is huge. And this can't resonate in a circle. How come? Tell me, please. sp3 can't resonate in a circle. Not aromatic. sp3 means not aromatic. ATIC. But if you can do this, where this reaches another molecule's H, I don't know why it's green, reaches another molecule's H, can't reach that one. I got to add something on that first arrow. You can't reach that H, it's on an atom next door. It makes a triangle on the way. Intermole. On that arrow, I need to see the word intermole or the short form intermole. And that's tautomerization that actually favors the enol. Why? Because the enol is aromatic. Every atom is sp2, 6 pi electrons, rings, good stuff. Okay. So I guess the Claisen rearrangement is this step. And if I had to name this, and I didn't want to call it tautomerization, I wanted to give it a better name. How about this word? Re-aromatization, because we started with something that was aromatic. This ring in the middle here is aromatic, right? We changed it to something that was temporarily not aromatic. And then we got our aromaticity back. So that's a nice word. Re-aromatization. I would expect that to be very fast. Plus facile, as they say in French. Very easy. Okay, and this would be slow. That's the one that takes your heat. There's your heat right there. No heat necessary for this last step. And that's the Claisen rearrangement for you. And we're going to stop that one right there.